So a thinner membrane have higher permeance, less area. And so what you find in the literature is people are targeting 100 nanometers as the thickness of the active layer. 100 nanometers, that's 1,000 angstroms, that's a very thin layer. And so the manufacturing of these kind of membranes is a challenge. How about with two components? Let's imagine a 50-50 feed of nitrogen and CO2. CO2 is selectively more soluble in the membrane, and so CO2 goes up here. Nitrogen is less soluble, it goes down here. And so you see in the end, the permeate in the end is very much enriched in carbon dioxide. And the separation happens because, first of all, this is more soluble. And you see the slope here is flatter than the slope here. That's your diffusion coefficient. Solubility and diffusion are the things you need to know and love to do membrane science. So it's actually easy to remember. Let's talk about diffusion for a moment. Cats actually swim very well in water, if you've ever seen that. But as you probably know, cats are not very soluble in water, if you know anything about cats. So while you would think that cats would move through the membrane well, they're not very soluble. So it's a way to keep in mind the difference between solubility and rates of transport. In most polymeric membranes, the diffusion coefficients are very similar. And it's really the solubility that matters, hence my illustration with the cat. And so most of membrane science is aimed at enhancing the solubility of CO2 inside the membrane. And the transports are more or less the same. So now you've designed your membrane and you have it in some elegant structure, but let's just take a flat surface. And so I have the flue gas coming in. And downstream, what's the right thing to do? Should I put a vacuum downstream to pull the CO2 through, or should I pressure the front end to push the CO2 in? So you're talking about compression versus pumping a vacuum, and which is the better way to go? So certainly compression is cheaper, it turns out. We know how to compress gases very well, and so that's a good idea. And if we pull a vacuum, we'll have only a CO2-rich permeate, and if we compress, we have to compress both gases. Downstream, we only have to vacuum one, so there's an advantage there to vacuum. Nevertheless, much of the industry relies on compressors, and here's a picture. These are enormous, these devices, and they're quite expensive. And they can be half the capital costs of a membrane separation unit and most of the operating costs. So nevertheless, it's interesting that compression dominated the field for a long time. And so really the goal is to lower the energy consumption in order to do carbon capture. So I'm going to review very briefly 6 ideas. I'm only going to cover 4 of them or 3 that some people in the United States who work for a company actually sat down and said, let's see if we can rethink how to do these membranes. So for example, here's a process flow diagram. Those of you who are engineers. This represents the membrane. Here's the membrane here. The gas comes in up here, and it's been pressurized by this turbine to 5 atmospheres. And so CO2 comes through the other side, and if you solve the equations for a typical membrane, you get almost 30% CO2 at 1 atmosphere. And the stuff on the high pressure side is recycled back to an expanding turbine that generates a little bit of power, and there's a little bit of CO2 coming out. So here's the costs here. The total energy is over 100 megawatts for a 500 megawatt power plant, and the membrane area is over 1 million square meters. That's pretty bad. That's 20% of the electricity production for a 600 megawatt powered plant. So the idea that Richard Baker and his colleagues had was, let's use vacuum instead of a compression. So here's that picture. Here comes the flue gas at 1 atmosphere, no compression, a little blower to just move the gas along. And now downstream, we're going to put a vacuum pump. And we get the same enrichment of CO2 as we did here. And look, its energy is half that, and the membrane area, though, is a little larger. Yeah? But nevertheless, in terms of energy consumption, the vacuums were a good idea. Another epiphany that was delivered by this community is to ask, what's the best way to flow a gas over a membrane? So if the membrane is flat here, flow the gas along here. But that's actually not how it's done. It turns out that's not the most effective way to maintain the largest gradient of concentration between one side of membrane and the other. There's a whole bunch of different ways to flow the gas. And so if you imagine now that the membrane is not a flat sheet but a cylinder, and I have one gas coming in here, and the exit coming out, and then another one perpendicular coming through the tube. That's a much more common way to do that, and you can rearrange all these flows. Engineers know how to do this, and the vacuum technology gave this, and they added these improvements in flow, and look, we've decreased the energy consumption even more, and now it's half the surface area, and look, we're already up to 40% CO2. That's not quite halfway to the goal. Very impressive. Okay, what else did Richard Baker and his colleagues decide to do? What they said is, rather than do this with one membrane, let's do it in 2 stages. And in one stage, I'll have a huge flow rate, and I have to process a lot of gas. And I'll make the selectivity of that membrane for CO2 less than optimal. And then the second thing will process a lot less gas, and so I can make the selectivity much higher. And in so doing, look, they get 97% CO2. This number is normalized to a different unit, so don't pay attention to that, but you do get 97% CO2. So the last idea they had is really clever. This is how complicated it gets. You don't have to understand all the details, but let's just walk through. Here's your burner. You remove the particles, and here you blow the gas over the first module, lower selectivity, and here's the vacuum pump. And then you'll pull the water out. That's easy to condense. And you compress it, and there's your liquid CO2 for sequestration at 90%. But the residual gas that comes off here goes to the second module, and rather than pump a vacuum over here, the authors came up with this idea, let's just take plain air and sweep it through. The difference in concentration of CO2 here and here is large because air has only 400 ppm of CO2. And this particular stream has about 2%. And so by doing that, they get a whole other set of contributions with this air sweep. And they feed some of the enriched CO2 back into the boiler, which makes the CO2 concentration higher, which improves the permeance here. And they make use of the water. Here's the answer. 16% of the power plant to produce CO2. Remember, we talked about 14% as the thermodynamic minimum, and the current amine processes are 30%. So if I were a betting man, and I was going to make a prediction as to which carbon capture technology is going to pay off in the long run, there's your answer, membranes. And that's why it's at pilot scale, and that's why the U.S. Department of Energy is focusing a great deal of their research efforts on pilot scale membrane science. Very exciting. So the U.S. DOE now funds it. So in summary then, the membrane separations for carbon capture really are limited by the pressure drop you can achieve with these huge volumes of flue gas. Remember, we fill the Empire State Building a few times an hour with just one power plant. Permeance is determined by diffusion and solubility. The most selective membrane turns out not to be the best. We didn't talk too much about details, but very clever process engineering can be used to achieve the best possible separations. So membrane science is really the way to go. And Richard Baker, reaffirmed that to make the better membrane, you didn't have to be a genius. You didn't have to invent warp drives or nuclear fusion. What you had to do is be very systematic and careful. I understand what's happening in the membrane, and I engineer and design them very well. So what I've tried to show you so far is that carbon capture can happen in 3 ways. Absorption into a liquid, off the shelf, ready to go. Adsorption onto a powder, opportunities for materials research not yet ready to deliver, at least for coal-fired power plants. And then membrane science has delivered really astounding engineering breakthroughs and is nearly ready to go. I just mentioned adsorption because while it's not competitive or feasible for direct capture, capture from a coal-fired power plant, it turns out for very dilute concentrations of CO2, adsorption turns out to be the way to go. The membrane areas are just too large. And so that reminds us that capturing CO2 at 400 ppm from the air is actually something that adsorbents can do. Another application of adsorbents that's emerging is the use of mitigating CO2 in spacecraft, in submarines, and increasingly in building design. So if you're, it's very hot outside and you invest in air conditioning for this building, what you're doing is you're taking air in and then you're pumping that cold air out. Wouldn't it be nice if you could recirculate a lot of that cold air? Well, what has to come out of the air in order for us to recirculate? CO2. So there's a considerable application in those areas as well. So that concludes the carbon capture part of where we're going. And now the next thing we need to do is talk about sequestration. So I'm going to get started on that. We'll get 10 or 12 minutes into that before we take our break. Okay? So let's go to geological sequestration. Now, we used to have some geologists in the room. Are they still here? Yes? Oh, good. Thank you. Thank you for staying with us so long. So we've imagined these great technologies. We're compressing CO2. It's in the pipeline. It's supercritical. And where do we go and what do we do with it? And so the idea is to use geological sequestration. Let me just say at the outset, because I know there might be some critics here, how come Reimer's not talking about putting CO2 in the ocean? That's because nobody's talking about it anymore. It's a really bad idea. Okay, let's just leave it at that. Okay? If you want to talk to me more about that, we can say that privately. So nobody's talking about putting CO2 in the water, seawater. Okay? We are talking about is making rocks. And so remember from these diagrams that as a function of depth into the earth, by the time you get about 1 kilometer underground, CO2, the natural pressure is that associated with supercritical CO2. So that's the fluid we're talking about underground. And we need to understand the relationship between CO2 with its rocks underground. And so I want to remind you of this other picture of Amritsar. The reason we are removing nitrogen from the flue gas is to decrease the area associated with sequestration of CO2, but you recognize it's a big number, and it represents a significant impact on the geology underneath the site at which you're pumping it. Really, I mean, are people actually imagining doing this, considering the volumes? So here's the point source emissions from a coal-fired power plant, from the USA for CO2, and that's the mass, that's the volume, and it's supercritical CO2, so it actually floats on water. And here's the amount of water the U.S. injects every year underground in order to either create power, but more importantly, to push more oil out for us to drive our cars. So if you look at these numbers, you recognize that we are already pumping underground a significant amount of fluid. So it's not a new notion that we would pump fluid underground. It's a notion that has already been exercised already. What about the scale of this sort of thing? This is a simulation. So this is distance in kilometers. So we're looking at a map of a part of the U.S. In the state of Illinois, in the center part of the U.S. And here you have wells, and you're puncturing, putting CO2 underground. And these are simulations on a computer of the pressure underground as a function of position in time. 100 years after injection, this is the high pressure plume of CO2, and it's in units of 12 here. And that's, I can't recall exactly what the units are, but you see it falls off. And you're probably asking yourself, that's a huge impact underground. That's completely unprecedented. And the answer is no, because here's the data for groundwater that has been pumped under that same basin. And you recognize there's the high pressure region right there, and the length scales are on the order of the same. So again, we've been pumping water underground for a long time. We've been measuring the physics of water underground. We understand that it's possible, and it's, so putting CO underground at these kind of industrial scales is not unprecedented. So what we need to know now are the 4 main mechanisms by which CO2 gets trapped underground. And of course, it's essential that we keep it there. We don't want a big plume of CO2 coming to the earth. We'll come back and talk about safety in a few minutes. So remember my picture, CO2 is pumped underground, and it exists there as a fluid. And this particular material here is called caprock. And what does that caprock do? So what we've done here is we've put CO2 into this region underground, which is largely brine, salty water and porous rock. And above it is this caprock, which has very limited permeability. And so it stays underground at first because it can't go anywhere. in the cap rock because the cap rock has holes too small to let the gas through. But you see I've drawn this so that because supercritical CO2 is lighter than water, it's going to float uphill. And I've drawn that deliberately because that's likely to happen in the real world. And so aren't you worried about this? I'm not. Maybe you are now, but hopefully you won't be worried as we move through this. So the first thing that happens, there are 4 mechanisms for this to stay underground. And the first thing that happens is called stratigraphic trapping, which is to say it just is blocked from going uphill. And so here's a picture of our CO2 plume in this brine aquifer, and it's trapped. So the first thing you need to do as a geologist is understand the geology underneath you and ask where are there layers of rock which have cap rock, we'll say more about its chemistry in a minute, and porous briny material underneath it. That's the target place where you can put CO2. Here's another picture of that. Here's the buoyant plume of CO2 in the brine aquifer, and right above it is here's the aquifer, and here's the cap rock seal. And it's even possible in some cases where the cap rock has a V shape, and so that's a natural place to put CO2. Why do we know about that? Because it's the natural place where oil accumulates. So whenever we pull oil out of the ground, it's probably a geology that's very, very similar to this. So for every well that we take oil out of the ground, it's a likely target for us to put CO2 into the ground. The next mechanism is called residual trapping. And this is an interesting one, and I'll show you a movie in just a moment. But of course, what's happening is the CO2 is going to float uphill, and behind it, the salt water intrudes into it. And so what you wind up doing is creating trapped bubbles of CO2. Here's a movie. This is a pore in a rock, and this fluid in here is water. And what you're going to see is CO2 come through this pore. So here comes the CO2, and it displaces the water, or brine, and there's the CO2 moving through. And then the brine next behind it, and because of differences in surface tension, you're left behind with a little droplet inside. That's a CO2 droplet embedded inside of this water. Okay, that's called residual gas trapping, and it occurs first after we've pumped it underground. Here's a picture here of a prediction of the CO2 saturation in a reservoir 10 years after injection, and you can see the concentrations of carbon dioxide in these bubbles. And then here's another cartoon which shows this residual trapping. What else can happen? The thing that should be most obvious to you is the CO2 dissolves in the brine water. That's just like the process by which we make soda water, and that's called solubility trapping. And the CO2 slowly dissolves into the brine. And then the last step is that the CO2 reacts with the rocks to form minerals like calcium carbonate, and those minerals will stay forever underground. They're lost to the atmosphere then forever. So that's the last step. And so the last slide before our break, actually second to the last, because I want to show one other thing. This is how much trapping occurs, how much capture occurs as a function of time in years. And so when you first inject the well, it's this structural or stratigraphic trapping that keeps the CO2 underground. And then it's necked off into these little bubbles that are residually trapped. Ultimately, they dissolve into the brine. That takes even longer. And then ultimately, they're trapped as minerals. And of course, as you go further down in time, the security with which the CO2 is stored increases. Mineral storage is the end point. It's secure for eons. And along the way, there are opportunities, which we'll come back to in a few minutes, for environmental risk, which we have to look at. So these are the 4 mechanisms. And just before your break, let me just go to my review questions for you. There are 4 mechanisms to trap CO2 underground. Name one. Okay. Well, it could be residual trapping, solubility trapping, mineral trapping, or stratigraphic trapping. Yeah? And so that's a review question for you to consider. Let's take our 15 minutes now for a cup of tea, And then we'll come back and continuing talking a little more about geology.